Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 18, and it is entitled Gravitational Potential Energy, Kinetic Energy, and Free Body Diagrams 2. This lesson is in 3 parts, 2 of which are closely related, and the third part is somewhat different. Let's begin with the topic of gravitational potential energy. Cast your mind back, if you will, to Lesson 11, in which we introduced the concepts of work, energy, and power. We spent most of that lesson concentrating a whole lot on work and only a little bit on power, choosing to wait a bit until this lesson to develop the concept of energy. You'll recall that work results from a special combination of force and displacement with the equation W is equal to F times D times cosine of theta. So if a constant force, F, which acts at an angle theta on an object, pulls through a displacement D, then we say numerically that the amount of work that's done on the object is the magnitude of the force times the magnitude of the displacement times the cosine of the angle that's between the force and the displacement. We also said that power is the time rate at which work is done. And mathematically, we write down the power formula. P is equal to delta W delta T. These are 2 very important equations that you're going to be using over and over and over again in this course. And so you need to learn them and be ready to use them. Now, let's focus on energy. It turns out that energy is an elusive concept. It is an indirectly observed quantity coming in a multitude of forms. So, for example, there's mechanical energy, and thermal energy, and chemical energy, and electromagnetic energy, and radiant energy, and nuclear energy, and sound energy, and other forms too. The question, what is energy, is difficult to answer in a simple, intuitive way. However, it is clear that energy is always an indispensable prerequisite for performing mechanical work. If somebody stopped you on the street and asked you, "What is physics?" what would your answer be? I hope you would answer that physics is the science of energy and its transformations. So while the concept of energy may be elusive, it's nevertheless quite central to physics, and we've got to learn how to grapple with it. For our purposes in this course, energy is a number that indicates something about how much useful work we can get out of a system. You may have heard of energy as being defined as the ability to do work. Well, that's captured in this definition, and we want to deal with it quantitatively. Certain physical principles govern how this number can evolve as the system advances with time, whether it's moving or changing or melting or doing something else. In physics, we want to learn what the natural guidelines are and how we can exploit those natural guidelines for our own purposes. In this lesson, we choose to focus on mechanical energy, which, roughly speaking, deals with the energies of macroscopic objects, and that's to say, objects that are big enough for us to detect with our human senses. Later in the course, we'll handle microscopic objects where molecules and subatomic particles like electrons and protons are involved, and these fall under the categories of thermodynamics and electromagnetism. Mechanical energy is the most common type of energy you'll encounter, and you're sure to get a good dose of it on May's College Board exam. Mechanical energy falls into 2 categories. They are potential energy and kinetic energy. Technically speaking, potential energy is the energy an object possesses because of its position or its configuration. It's called potential energy because the object has the potential or the possibility of doing work if I release it. In other words, if I let the object go, it could exert a force on something that it collides with, pushing it through a distance. And of course, work involves both forces and distances. It turns out that potential energy further falls into 2 subcategories, namely gravitational potential energy and elastic potential energy. We can illustrate this with some diagrams. I have a couple of pictures here, 2 familiar systems in which potential energy is essential to their operation. A roller coaster makes use of gravitational potential energy in order to give the riders a thrill. There are all sorts of energy conversions rapidly taking place in this system. The rider in a roller coaster has mechanical work done on her by a motor that tows the car to the top of the first hill, which, by the way, is the tallest of all the hills. That work causes the rider to increase in her gravitational potential energy because she increases her elevation. As the rider rolls down the hill, she converts her gravitational potential energy into kinetic energy, the energy of motion, which we'll have more to say about in a few minutes. As the rider negotiates successive hills along with twists and turns, she's going through a constant exchange of various forms of energy. It turns out that nature governs her possible motions with some important principles, one of which is called the principle of the conservation of energy. And we'll learn to handle these physical laws as this course progresses. So, technically speaking, gravitational potential energy is the energy a system possesses due to its position or its configuration within a gravitational field. In order for the rider to experience her thrill, the car she's riding in must be strategically positioned in the presence of the Earth's gravitation, so that at some points she's elevated higher, at some points lower in the gravitational field. The roller coaster track has hills and valleys to position her in these various ways. The second form of potential energy is called elastic potential energy, the energy which a system has because of its deformation. The second picture illustrates this, in which an arrow in a stretched bow gains elastic potential energy because the bowstring is deformed from its natural position. We'll have a lot more to say about elastic potential energy in lesson 25, and so we'll leave the topic here for the moment. Now, let's go back to gravitational potential energy. Mathematically, we're going to symbolize gravitational potential energy using the letters PEG. PE means potential energy, and the subscript G means gravitational. Let's suppose that we set a reference level even with the ground and say that any object on ground level has zero gravitational potential energy. Now, let's take an object of mass m that's elevated a height y above the ground. In your textbook, your authors use the symbol h for height, but I like the symbol y better, and so that's what I'm going to use in these notes and the problems that follow. We say that the object possesses gravitational potential energy because it's elevated above the ground in a gravitational field. Numerically speaking, the amount of gravitational potential energy an object has equals a product of its mass in kilograms, acceleration due to gravity, g, is 10 meters per second squared, and its elevation, y, in meters. This is an important equation. PEG is equal to m times g times y, and you're going to need it for problem solving. It's a good one to put into your memory. The SI unit for energy involves a combination of kilograms, meters, and seconds, and that combination is kilogram meters squared per second squared, which is called a joule. This unit is named in honor of James Prescott Joule, a 19th century Englishman who investigated the relationship between work and heat. We always measure the elevation with respect to some reference point. In most cases, that reference point will be ground level. In many cases, it's going to be the lowest point that the system undergoes as a process of its motion. If I lift up an object above my head and let it drop to the floor, it's going to have a different gravitational potential energy than if I had let the object drop to the top of a table instead. So reference level is important. Because the gravitational force is a conservative force, it is possible to write down a potential energy function for it. And that's what we've just written down. PEG is equal to m times g times y. To say that the gravitational force is a conservative force means that the amount of work it takes to shift the object from one position to another within the gravitational field does not depend on the path that the object takes between the beginning point and the ending point. That's a technical definition, and we'll have more to say about conservative and non-conservative forces in a future lesson. Now, let's solve a numerical problem.
It's example 18.1, which appears on page 133 of your textbook. A 20-kilogram block is pushed slowly to the top of a frictionless 30-degree incline that is 6 meters tall. In part A, what is the increase in potential energy of the block? And B, what minimum force is required? Now I'm going to sketch a diagram of this, and then we're going to solve this problem. Let me make a remark here, though, that the fact that the plane is frictionless is important if we're going to figure out what the minimum force required to get it up the plane is. And in fact, this isn't going to be an example of a simple machine, an inclined plane, in which we trade in the force that we exert to get the object lifted with the amount of distance it takes to get the object to the elevation that we wanted. So here's my incline. With respect to the ground, the top of the incline is 6 meters above where the object starts when it's at the bottom of the plane. Here's my object at the bottom of the incline, and now I'm going to drag this object to the top of the incline. Here's the object at an intermediate point. I'm pulling the object up the incline with a force that's parallel to the surface of the plane. It's going to be that force that I'm going to try to calculate as I drag the object to the top of the plane. And now there's the object at the top of the incline. And we're trying to figure out what the gravitational potential energy is with respect to the bottom of the incline. Now the distance that counts is going to be the vertical distance through which the object moved. And that vertical distance is this 6 meters from the top of the incline to the bottom. That's 6 meters. So I'm going to put it into my gravitational potential energy formula and make that calculation. I'm using y to represent the elevation. Your textbook uses h. They mean the same thing in this context. I know what the numbers are, so I'm going to put them in. And now I get that the amount of gravitational potential energy is 1,200 joules. Now the force that I use to pull the thing up the incline is going to be related to the amount of work that's done to get the thing up the incline. And the amount of work that's done is going to be equal to the force times the distance that I drag the thing. The distance is the distance along the incline, like so. And that distance is going to represent the hypotenuse of a right triangle whose angle I know and whose height I know. So I could use the sine function to figure out what that distance is. So the sine of 30 degrees is equal to the opposite side of the triangle divided by the hypotenuse. The hypotenuse is the distance d that I want to figure out. So I'm going to solve that equation for d. And now I'll put in the numbers and get some result. The distance that the object moves up the incline is 12 meters. Now, we're going to see something in a future lesson that's called the work-energy principle. And the work-energy principle basically says this. The amount of work that I do on the object is going to be equal to the change in the object's energy. In this case, the amount of energy is the potential energy that's going to change. The object has 0 joules of energy at the bottom of the incline. It has 1,200 joules of energy at the top of the incline, and so I can set those two things equal to each other. Here's a little caveat. The work-energy principle is going to be modified in a future lesson, and we'll talk about how that modification occurs to include non-conservative forces. But first we have to understand what conservative forces are before we can add the non-conservative forces. So let me write the work-energy principle. The amount of work that's done is equal to the force times the distance. Now, that force is the force that is parallel to the displacement of the object. And we found that displacement along the incline to be 12 meters. That work is equal to the change in the gravitational potential energy. And whenever we have a change in something, that's equal to the final something minus the initial something. So I can write another step in my equation that says the force times the distance is equal to the final potential energy minus the initial potential energy. Now I know what the final gravitational potential energy is. It's 1,200 joules. The initial is 0 if we measure it with respect to the ground. The displacement is 12 meters. so I can solve that for the force. And now I can put in the numbers. And my final result is that the force that it takes me to pull this object up the ramp is equal to 100 newtons. That's the first part of this lesson dealing with gravitational potential energy.